welcome back, everyone. So, a couple of notes first. So, I had announced already that we were doing, or I was doing, open office hours, and apparently, oops, let me actually just get rid of the notifications. Yep. And well, but someone pointed out to me that I had misconfigured, and so Zoom sometimes would reject you. And I'm actually I was a little bit wondering why only a handful of people had registered, because in the past when I ran these, I had I had more people registering, and this time I had I announced 2 dates. I advertised it quite well in advance, and I had literally a handful of people, and I thought that was a bit disappointing. But then someone pointed out that if you'd get here to the registration, and then there was, depending on whether you were signed in or not, you'd get this very bad error message. And but I fixed that, with a couple of days to go. So this will be in about so the first one will be about half an hour earlier than the stream, and then there's a second one in 2 weeks, which is in my evening, so that's the European morning. So wherever you are in the world, there will be some of either the one this week or the one in 2 weeks. One of these sessions will be good for you. Right. Maybe I'll just post I'll just post this on the chat. How do I do that? Yeah, I'll just post it here. Yeah. There it is. All right. Okay, so with that, let's go back to ARGs, to antibiotic-resistant genes. So, I wanted today to maybe go over something a little bit different, which is ARG-norm. So we've seen ARG-norm. We've seen ARG-norm a lot, or as we've used ARG-norm, but in the last month or so, so Vedan Pramji was here in Brisbane, he's from Chennai, India, and he was here, and we worked actually quite extensively on that, and we've made a lot of progress. But I wanted to go over what that is, so I'll put out the caveat that most of this is indeed Vedan's work, not mine. Actually, so this is now ARG-norm. So this is also, so this is a different project that we have on GitHub. So you can, and so this has shown up on the stream several times because we've used this, and we use it to normalize antibiotic-resistant genes to the ARO ontology, to the antibiotic-resistant ontology from CARD. So, and the problem it solves is that all of these tools, they will output in their own private ontologies, not even ontologies, their own private vocabularies, and so we want to map them. Map them to ARO, to first of all just normalize things like different ways of spelling the same thing. So TETx, so you can spell a TETx like this. It can be TETx all uppercase. That would still be quite trivial to normalize, but it could be TET-X, TET parenthesis X. But sometimes it's not even the same name. And more importantly, once we mapped it to the ARO ontology, so ARO it's not only a controlled vocabulary, which would already be quite useful. A controlled vocabulary is perhaps the first easiest type of ontology, but it's already really useful. When we have when we have arrow, we also have more information. So I was trying to make this bigger. Right, no. All right, so in this figure you can't maybe not see it so well. Open image in new tab. But not only do we have these arrow numbers with some and their names. All right, let's just go back to this one. So we have this, that x corresponds to this arrow number, which is an identifier. So it's 3000205. That corresponds to that x. And then there's more information. So for example, it's linked to specific drugs that it inhibits. And those themselves have arrow numbers because that's also a controlled vocabulary. And then they are also not just individual drugs, but they can be classified into drug classes. So there's a structure there. And so once we go from whatever output of your tool is to arrow, then we've tapped into this larger vocabulary. Right, so, all right. So the idea argnorm is actually quite simple. So the idea is we have these mapping tables. So it's very simple. You have a mapping table. For example, here's and we looked a bit at ResFinder. Here's the ResFinder arrow mapping, and so this is the identifier that ResFinder uses. This is the identifier that card uses. So you can see that, probably this is correct because R2 and R3 and maybe this one is not exactly perfect. Sometimes it also happens that maybe this it's not exactly the same vocabulary. And this is the arrow identifier. So if you have output from ResFinder annotation that has this identifier, then we can use this table to map it to this arrow number, right? And we actually have done this for several of these databases. You can see, for example, here's arg and ot, and you can see, for example, here MCR 5.2 got mapped to MCR 5.2. And a lot of this you can eyeball, and for a human this is not very difficult, to match that this matches to that one. But to do it in a machine-wise, it's a little bit more complicated. And also, finally, there's two steps to this. So first of all, we try to use this. We try to do annotation using the RGI, which maps genes to the card database. So if we map the ResFinder database to card, then we can. That was the file I showed you before. But then that doesn't work 100%, and so the other thing we do is, this is a bad example apparently. The other thing we do is we add manual curation. So in a handful of cases, the automated system was not able to find, for example, this is another tool, DeepARG, so that this gene in DeepARG had not received an automated annotation, and then through manual curation, it's mostly Svetlana and Vedant, determined that this actually corresponds to TET-U. In this case, basically looking the name matches. Some of them might not be as immediately obvious which one would be the right identifier. In some cases, that maybe the exact sequence is not present, and so we need to find another one. So I wanted to maybe just illustrate some work we did on trying to understand ResFinder, the ResFinder database. So let me go back to here. So I'm working on argnorm, and actually, let me. Okay, so this is actually a version of argnorm without anything else, without any of my changes. So just to be extra sure. Yep. Okay. So there's a database, there's a file here. So there's a subdirectory called db harmonization, and this actually originally this code was written by Finley McGuire, and we've since adapted. So so it's no longer. So we've taken it a bit further, and there's this file. Okay. Which is a jug file. Okay, I'm actually just going to run it. Okay. So what this is doing, it's retrieving the databases from ResFinder. In this case, I commented out everything except ResFinder. So it's going to yeah, I'm gonna. So this has so it's retrieving these databases, downloading them, and now we'll run RGI on this, right? And then oops. Yeah, so. And so, what is ResFinder? So this is ResFinder, right? So this is a FASTA file, and you can see it's a nucleotide FASTA file. And when we see this, it actually took us a while to understand exactly what we were looking at, because many of these do seem to be coding sequences. And if they're just coding sequences or CDSs, then we can translate them to we can translate them to the amino acid version. And in fact, so for example, these top ones, these are just genes. So these are just coding genes, coding versions of genes. And so in this case, we should treat these as, we should translate them and then treat them as the amino acid versions. So this, however, if I do all of them, you can, and now if we look through them, most of them, in fact, are genes. So here in this case, this tool FNA to FAA just translates and it puts this star to mark that it has a stop codon. So most of them, that's exactly what we see. But then when we first looked at this, we saw that there were some exceptional cases. So for example, this one, there's some exceptional cases. This one has a bunch of stop codons. So what? This one has more stop codons. This one is a long sequence with a lot of stop codons. This one again, a long sequence with a lot of stop codons. So actually, so when we checked this, we weren't looking too closely at first. It just seemed, oh, okay, this is something more than just. This is something more. This is not just a database of CDSs. Then, what it turned out is that, in fact, so let's just count again. So there's about 6,000 genes. Oh, I think there's this might be still. Is this an old version? Oh yeah, sorry, this is an old version. Sorry, this is an old version. Sorry, sorry, this is an old version, and let me just clean this all up. Let's do this again. I'm gonna comment everything except the REST Finder. So maybe I'll just go. So this is a JUG file. You can see so it defines here these functions at the beginning. So there's this create out tiers, download files, and then has all of these simple functions that basically download. They download files, right, and then to get the different databases. So the MCBI database, there's a little technicality, we need to fix it, and then it runs RGI, and then finally it processes the outputs and right, and moves them to the right place. So here, create the outputs, then for every database run RGI and move the mappings. Right? Let's just execute. I'm going to execute in the background. Okay, blah blah blah. Oops, sorry. Yes. All right. Yeah. So this is actually that was an interest. So we have 3,000 genes, and as it turned out, almost all of them are really just genes. So all of them, if we took the nucleotide version, we translated with this tool FNA to FAA, and we get just a perfectly well translated gene with a stop codon at the end, and that's it. Except a handful of cases, and so when we looked more closely, we saw that indeed it was just a handful of cases, right? And what happens is that there's these Van hacks. And so what are these? So these, and there's about 40 of them. 40 out of 3,000. So a little bit over 1% are gene clusters. So in the original sequence. So actually here, this seems to have, there's a gene and then some, so there's multiple genes in this sequence. And actually, just by looking at it, we can see that it's longer than the other one. So here you see this one, this is a full thing, it goes on and on. So 56 line, as opposed to this more typical gene, which is only 11 lines, right? So most genes are. This is a normally sized gene. I don't know exactly what that means, but this is a normally sized gene, and these sequences, they're just longer. And what we realize is that in fact they correspond to multiple genes. And so now comes the question, so what do we report here? And so if we're thinking that what a user has, So if a user has, say, a hit here because they've, for example, in the metagenome, they have some sequence that aligns with this, with this sequence here, with this Van Hax PA1. So they've assembled their metagenome, and now they've used whatever tool to blast against ResFinder. Maybe they just use blast directly. And now what? Now I think the truth is we now don't even know exactly. So if we just know that it hit this gene, if we know it hit this sequence, all we know is it hit this cluster. So we can no longer really distinguish genes. We have to give a cluster like, sorry, is there a problem with the stream? I think there's some problem with the stream. So the user, so if the user has a hit here, what we will see is that there's not enough information to know more than we've hit this cluster. Oops. And so the best we can do is hit the cluster. And now I think there's something with my internet. Something. Okay, this seems to be buffering. Okay, I don't, because I see that the video is frozen, so I'm not even sure if this is doing anything at all right now. Let's see. So if this doesn't improve in the next couple of minutes, I might just stop, because there's really not much I can do. My internet connection is working, so there's unfortunately, and I see it frozen. Okay, I'm gonna be ending the stream. I see this complete. I see myself frozen on the other window, and so yeah, I don't know what else to do at this point.